Hi guys, welcome back to another video. Today we're going to be looking at the following LCM and GCD problem from Mathcounts 2021. And so the problem is shown below. How many ordered triples of positive integers a, b, c have the GCF of the three integers as 2020 and the LCM is 2020 squared? Okay, so my first strategy of attack for problems like this is whenever you have GCF and LCM, you're always going to consider the factors of a number, the multiples. And to do that, I like to look at the prime factorization of a number because that usually tells us a lot about the problem. So if we prime factorize 2020, we would find that the prime factorization is 2 squared times 5 times 101. And we can do that pretty quickly because 2020, that's not too hard to tell that that's just 101 times 20. And 20 is 2 squared times 5. So the prime factorization is 101 times 5 times 2 squared. And we also see we have the LCM of the numbers is 2020 squared. So 2020 squared is the LCM. So if we prime factorize this is just every exponent times 2 for our prime factorization of 2020, right? Because we know from our exponent rules that squaring a number is the same as multiplying its exponent by 2. Okay, so now we have three integers where their greatest common factor, which again is the largest number that evenly divides all three numbers, is 2020. And then the LCM, which is defined as the smallest number that's a multiple of all three numbers, is 2020 squared. So first things first, we know that the three numbers, if we write them down, A, B, and C, so they all have to be some product of powers of 2, 5, and 101. And there's some powers to these that we don't know yet. But they have to be something like this. Because if you think about it, if I have any other factors, then that means my LCM will have to be larger because our LCM is only divisible by the numbers 2, 5, and 101. So for example, if A was 2 times 5 times 101 to some powers times a 3, for example, this wouldn't work because then our LCM wouldn't be 2020 squared because 2020 squared isn't divisible by 3. So there's no multiple of A that would go into 2020 squared. So that basically tells us that all three of our numbers have to be some product of the factors 2, 5, and 101. Now, if we look at our prime factorization, we see that the GCF is 2 squared times 5 times 101. So we could take each of these prime factors individually, right? It's basically three mini problems. So first we consider the 2's, and then we consider 5's, and then 101's. So if we start with the 2's, our GCF tells us that we need 2 squared in we at least need 2 squared in each of our three integers, right? If I only have 1, 2, and A, then our GCF wouldn't be divisible by 4. So I know that if I call these exponents, let's say x sub A, x sub B, and x sub C. So xa, xb, and xc all have to be at least 2, right? And moreover, we need at least one of these numbers to be exactly 2. Because say they were all 3, then our GCF would actually be 2 cubed times something, right? If all of our x's were 3 or larger, then our GCF wouldn't be 2 squared, it'd be 2 cubed. So we know that all of our powers on the 2's have to be greater than or equal to 2, with one of them being equal to 2. And now with the same logic, if we look at the LCM, you know that the maximum power on the 2, so the max value for any of our x's has to be 4, right? The maximum has to be 4. And if I do, for example, if I do 5, then our LCM would have a 2 to the 5th, not just 2 to the 4th. And then similarly, one of these values has to be a 4, because if all of the values are less than 4, so say 3 again, then our LCM wouldn't have a 2 to the 4th in it. So basically, we need to find some arrangement of x's such that they satisfy this condition, one of the x's is equal to 2, and one of the x's is equal to 4. So x sub I and x sub j, if we say. So this, it seems kind of complicated, but if you write this out, you'll see that it's not too bad because we can just list it out really. If you have x sub a is equal to 2, for example, right? X sub a could equal 2, x sub b could equal 2, and x sub c could equal 4. Or I could have 2, then 3, then 4. Or I could have a 2, a 4, and a 4. And obviously, I can rearrange these in any way. So I have 3 possible cases here. And I could rearrange them in any way. I could do xa is 2, xb is 2, xc is 4. Or I could also switch the 2 and the 4 and make xa 4, xb 2, and xc 2. So the ordering we have to account for, but these are 3 possible scenarios: 2, 2, 4, 2, 3, 4, and 2, 4, 4. Because we know that our smallest has to be a 2 and our largest has to be a 4. So those are defined and we can't really change that. So now a 2, 2, and a 4, I could arrange this in 3 ways, right? The 4 can either come first, second, or last. And same with the 2, 4, 4 in case number 3. I have 3 ways to arrange these because the 2 can go either first, second, or last. And now the middle row, case 2, this actually has 6 possible arrangements, right? There's no repeated digits, so it's just 3 factorial, which is 6 possible arrangements. So ultimately, we have, for our 2's, 3 plus 6 plus 3, we have 12 different ways we can distribute the 2's to one another, to each of our 3 integers. Okay, so that takes care of the 2's. Now we do a very similar process for the 5's. Right, so if we call the exponents on the 5's using similar notation, y sub a, y sub b, and y sub c. So with the 2's, we use 2 and 4 as our bounds because the LCM and the GCF were 2 squared and 2 to the 4th. With the 5, however, our bounds would just be 1 is less than y sub a, y sub b, and y sub c, which is less than or equal to 2. And again, one of the values has to equal 2, and one of them has to be 1. So really, I could do 1, 1, 2, or I could do 1, 2, 2. And similarly, these both have 3 ways to arrange them, right? The 2 could either go first, second, or third in our first case, or I could put the 1 first, second, or third in the second case. So ultimately, for the 5's, we have 6 ways to arrange them, right? There's 6 ways to arrange the 5's. And now the 101, if we call it ZA, ZB, and ZC, we can do the same thing, but notice there's no difference between the 5's and the 101's. It's both of them have a power of 1 in the GCF and a power of 2 in the LCM. So the only thing that changes is the base, 5 versus 101. But that doesn't matter. We know that the calculations will still be the same, and we'll still get 112 or 122 in some ordering. So there's going to be 6 ways to distribute our 101's as well. And now because we have, so this basically tells us these numbers 12, 6, and 6, that we have 12 ways to distribute our 2's, 6 ways to distribute the 5's, and 6 more ways to distribute 101's. And now to finish up the question, they're asking for how many ordered triples are there. We would just multiply these, right? Because each of these presents a new case, and we wouldn't add because it's not like an or. I have 12 possible cases for the 2's, and I have 6 cases for the 5's, and I have 6 cases for the 101's. So our answer would just come from multiplying 12 times 6 times 6, and this we can do, right? So this would just come out to 432. And so that's our final answer. Let's circle that in red. And that would be it for this question. So this question definitely looks very daunting, but if you look at the case-by-case examples and you just realize that prime factorizing the numbers is a great place to start, it's definitely doable. So that should conclude today's video. If you have any questions, please leave a comment down below. And if you enjoyed the video or found it helpful, a like or subscribe would really help. And I will see you all again tomorrow for another problem. Thanks, Devin, for joining.